now, so I'll start sharing slides anyway. I have to do that via desktop, so I won't be able to see any of you.
There's always a bonus to everything.
Yeah, that's probably a good thing.
So if you do want to say anything, don't use, you'll have to say it, I'm afraid. Chat I won't see either. Right, let's see if this works. You should now see an IBM webpage.
Yep.
And now we'll go to slides.
Yep.
And you should see the full slides.
Yep.
Great. Okay, so in a good tradition, what am I going to talk about? Going to start off with why do we need quantum computers, a little bit about the origins behind quantum computing, one of the ideas behind the actual computer side and what does it have to do with cats, and then looking at programming quantum computers and where to go from there. And I'll just say why I'm talking about this. It's one of the wonders of lockdown and also being retired is you have some time on your hands. So a long time ago, when I used to be a pure mathematician, I did some work in things called Hilbert spaces and such, and they relate to the quantum area. So I also had a lifelong interest in sort of high performance computing. So I thought now would be a good time to look at those two together and look at quantum computers. So I'm kind of starting from that basis of this looks interesting. Let's find out a little bit more. But first thing, quote from Arthur C. Clarke, famous quote, any sufficiently advanced technology is indistinguishable from magic, which is hard to say. At first glance, certainly areas like quantum computing kind of, to me, looked a bit like magic. It's only later on you start to realize it's not. It's just another way of doing things. We'll come back to that later on. So why do we need quantum computing? Slightly busy slide this. Let's bring up the little laser pointer. Well, I suspect everybody listening knows about Moore's law, which it basically talked about in 1965, the doubling every year of the number of transistors on a chip. And that was revised later on to doubling of transistors on a chip every 2 years. And remarkably, Moore's law is held up quite well over the period. And if you look on the right-hand side, it's kind of doubled as expected every couple of years. And as a comparison of what that means, when I was at university, back in the 1970s, early 80s, being kind to myself, I brought my first microcomputer, Acorn Atom, that had a 6502 running at 1 megahertz in it. That had 3,218 transistors in it, and it was made out of 8-micron technology. And going back to Arthur C. Clarke's quote before, to me, being a mathematician, how that 6502 worked, or more specifically, how people designed it, seemed pretty magical at the time. Many years later, not so much so, because 3,000 odd transistors is very low, and actually the complexity of the processor is actually quite simple. And there are people today that at home will design their own processors of similar complexity on FPGAs, and it's kind of not as magical as it used to be. But life moved on, and if you take something like one of the latest processors that you could put in a PC, the AMD Ryzen 5 8000X, that's got 4.15 billion transistors. So it's a little bit more complex. It's basically 1 million times more transistors than we had in the 1980 microprocessor. And it's based on a 7 nanometer technology. Now, microns are 8 to 10 to the minus 6. Nanos are basically 10 to the minus 9. So you've had that 1,000-fold decrease in size, which has resulted in 1,000 squared, basically a 1,000,000-fold increase in transistors. So it kind of fits in nicely with Moore's law. The problem is, and this is kind of talked about almost every year, this won't continue. And one of the reasons for that, as I've mentioned earlier in the slide, we're getting to the limits of what you can do with silicon. So a silicon atom is 0.2 nanometers in size, and 7 nanometers isn't that much bigger than that, 35 times larger than that. So keep on expecting to get to the limits of really what we can do using very small numbers of atoms. Now, to everybody's surprise, IBM just recently announced they'd done a 2 nanometer process. And with that technology, they expect to get around about 50 billion transistors on. That's not going to be coming to a PC anytime soon, but that 2 nanometers really is getting to the point where it's unlikely it'll get much smaller than that. And there are lots of effects start to occur when you get down to this size. Transistors stop working as well as they should. There's an effect called quantum tunneling. And if you think of a transistor being like a door that when it's closed, it won't let electrons through. When you open it, it lets them through. Irritatingly, quantum tunneling means that sometimes the electrons will just jump from one side of the door to the other without it actually being open. And that means your transistor starts to have errors. And as you get smaller and smaller, this effect occurs more often. So this time it really does look like we're getting to the limits, certainly of what we can do with silicon. There are other materials out there, but this is probably kind of where Moore's law starts to tail off. And we need to look for other technologies to speed things up. Now, part of that is obviously been, and the way we use all those transistors now is through parallel processing. So we have multiple cores on a single chip. You may have 16 cores running concurrently, so you can process that much faster. But if you're running out of transistors on a single die, that is going to also reach its limits. So that's where we are now. Oh, I should say it popped up yesterday on my phone. My phone obviously thought that it was actually quite capable of doing almost anything. So it came up, my antivirus check on my phone decided the universe is safe, which I think is slightly exaggerating the power of my phone, even though it's considerably more powerful than the supercomputers of the 1980s. So, carrying on, why do we need quantum computers? Well, on the left-hand side, the sort of academic justifications for quantum computers come down through machine learning, material simulation, chemicals, and molecular design is a really important area. If you want to simulate the design of chemicals, you've got to simulate how the electrons basically fit together between the different atoms to make up the molecule. And the complexity of that explodes exponentially. So it's an incredibly difficult problem to do anything but simulate the simplest chemicals. If you can do that, you lead on to drug design in areas such as that. But in a different direction, also financial modeling. And it's an area that quantum computers, lots of interest is being shown, because financial modeling is all about assigning probabilities to different events that may occur with constraints and trying to model what the outcome is. And those models become very quickly complex and can take up large amounts of current supercomputing time. Next one is the one that tends to hit all the press, and that's a combination of cryptography, communication, and espionage. And probably the thing that people have talked about most about quantum computers is their potential capability to crack RSA encryption. And of course, RSA encryption is used in practically everything we do, through the financial system, saving stuff on my hard disk even is encrypted in that sort of way. And we'll come back to that later, but certainly quantum computer does provide an opportunity to crack that kind of coding. It also provides the opportunity to encode things in a way that will not be cracked easily. So it kind of takes with one hand and gives with the other. Logistics, scheduling, again, kind of big problems. I put next to scheduling timetabling because just thinking of university environment, timetabling is never perfect. And it's because scheduling problems are really difficult. You have lots of information with lots of constraints, and finding an optimum solution is really difficult to do. So you end up with suboptimal ones, which bluntly don't satisfy most people most of the time. And finally, there's physics modeling, and that's modeling of how the universe works. And that certainly for physicists is a very important area, understanding how their models work against reality. On the right-hand side, I went to look at one of the main manufacturers of quantum computers, a particular type of quantum computer, D-Wave, and they've obviously got a similar list to the left-hand side, but they've got over 250 early applications and people using their computers in these areas. And I was quite interested to see the last one that included internet advertising placement. So I'm not sure if that's good use of quantum computers, but it's certainly an interesting use of trying to find the optimal way to place adverts to get maximum returns. Right, so what sort of problems, why can't we just use the computers we've got? Well, first example is just a very simple one. Many people use it. I've taken this one from IBM, and it's basically around seating 10 fussy people at a dinner party. And it just demonstrates an exponential explosion of the problem. So you're running a dinner party and you got these fussy people, and there's only one good way to sit them all. So typical example would be a wedding. There's only one way you can sit everybody so an argument won't happen. Right. If you've got two people, it's relatively easy. You've got one sitting above, one sitting below, or vice versa. They're kind of the same, but for now we'll consider those as different cases. If you go to 5 people, you suddenly go up to 120 different ways of doing it. If you go to 10 people, well, you can't see it in the diagram. There are lots of little tables with lots of little people there, and you're into the millions of different ways of doing it. In fact, it goes up as n factorial, so it explodes the numbers. And if you are looking for that, the search for that is going to take you a long time. And if you imagined having 100 people, then 100 factorial is going to actually, put some real pain to any existing computer systems. So that's one example. The other, coming back to encryption, is basically some people would like to break encryption. And RSA encryption, in its simplest form, it uses a large number that is the product of 2 primes. And to break the encryption, if you've got the big number, then you've got to factor it into the 2 primes, and then you can break the encryption. And that turns out, when the numbers start to get this big, to be a difficult task. And if it gets to, if people can start to do that, you just make the numbers bigger. But quantum computers do give the potential to break these codes. They work on a principle, a particular algorithm developed by Shaw that allows a lot of parallel computation to occur to try and get candidates for the 2 prime numbers. So something that might have taken months, even years, could potentially be done in hours or even minutes. So there is a real potential there for breaking the encryption system that basically runs the world for us. However, should note that the financial areas specifically are very aware of this, and actually slowly different encryption techniques are being used to move away from this. So if quantum computers do appear, then that should be not such a problem if we move over to those new encryption methods, or we could move over to quantum encryption instead. So I'm going to just do, this is going to be the sort of foundations of where quantum computing came from, and it goes back really to 1801. And in 1801, Thomas Young did the double slit experiment, or the equivalent to the double slit experiment. And up to that point, people believed that photons were composed of, well, little elements, little particles. And he did an experiment with, first of all, one slit, and he fired photons through it, and he got this distribution coming out on his screen here, which kind of looks a bit like you would get if you threw tennis balls through a hole. They kind of come out mostly round here and then slide off to either side. He did a similar experiment with another slit, and he got the same shape. And then he did it with 2 slits very close together. And what you would expect, if it was particles, that what you would get is the hump here and the hump here, 2 distinct areas. And that's what you would get if you threw tennis balls through 2 holes. You would get 2 humps around each hole. And he didn't get that. And this is familiar, really, I think, to almost everybody. What he ended up getting was an interference pattern. So he got large amounts of light here, less light here, less light here, but dark fringes in between. Very much like the effect you get dropping 2 stones into a lake, where you get reinforcement of waves where they're in phase and destruction of waves where they're out of phase. So nowadays, a fairly well-known result, but it caused a lot of problems at the time, because all these people that believe in the corpuscle approach suddenly got a little upset that it didn't seem to work, and now they were going to have to move over to thinking of light being waves. And there were competitions held to prove Young wrong, and he actually kind of gave up largely doing physics and concentrated on his medical area because he got so much heartache from it. Sort of the equivalent in those days of social network sort of being attacked on that. So he moved away from the field. But as time went by, it was kind of accepted that waves were the way to go. But something weird was happening, and we'll see later how weird. Right, we jumped to 1901 and Max Planck. he was looking at what's called the Rayleigh-Jeans law, which basically talks about the spectral radiance of electromagnetic radiation, which is, in a simple way, saying the energy emitted from a black body is proportional to its temperature divided by the fourth power of its wavelength. And the key here is what was noticed and what was called the ultraviolet catastrophe was this law didn't work at high frequencies. And it just really did not give the right results. Now, this is not uncommon in areas like physics, because basically you propose a law or model and it holds for some time until somebody does an experiment and it doesn't work anymore. And then you come up either with a modification to that law or a brand new law. And that's how physics moves on. So Max Planck saw this and he looked at it, and how could he adjust that formula to work? And what he concluded was, if he considered that the radiation was emitted not as waves in this case, but as little quanta of energy, kind of particles, it worked. He could make an equation that actually mirrored reality. So that's what he did. He didn't like it. He didn't think it was reality. He thought it was a trick that just made the maths work. So he was still a great believer in the wave theory, but introduced particles back in his mathematics. Not much later on, Einstein did work on light, and he basically deduced that actually quanta really did exist, and they did reflect reality, these little packets of energy, later to be called photons in the case of light, and not just a convenient way of making the equations work. Well, that kind of introduces an interesting point as far as light's concerned, because it means that some of the time you've got to think of it as particles, some of the time as waves. Right. A little later on, Ernest Rutherford had developed his planetary model of how atoms work, which I'm sure most of us were taught at school if we did physics at GCSE, which basically gave the impression that you had a nucleus with electrons going around in nice little orbits, just as the solar system works. As a side, it's one of those examples which is really irritating, because once, certainly in my case, once I've seen it, I think of it as really difficult to visualize it any other way, even though I now know that's not exactly what's happening. But that was his model. And one of the problems was the behavior of electrons and how they fitted into those orbits. And Niels Bohr came along and he came up with a theory about how those electrons were restricted to specific orbits and how they could jump from one orbit to another. And he used this, and this explained how spectral lines occur in spectroscopy. If you, again, probably remember back, if you do a spectroscopic analysis of different chemicals, you get black lines appearing, and they relate to how the electrons are in the atom for that element. So Niels Bohr did that, and that was the foundation of really quantum theory, quantum mechanics. And then, somewhat later on, Louis de Broglie, he showed that, really back to what we were talking about earlier, waves can exhibit particle behavior and particles can exhibit wave behavior, but not just light. For instance, electrons can exhibit wave behavior as well. In fact, it's been shown that larger collections of atoms can also exhibit wave behavior. So there's this strange duality that we don't see at our macroscopic level, or normally don't see, that actually things that seem solid can also be behaving like waves. And this is really key to quantum computing. Right. 1926, Schrodinger developed his equations that describe quantum mechanics. And whilst he did that, he also introduced ideas about how particles can be both, or say photons, can be considered both as particles and waves on a strong mathematical foundation. But he also introduced the idea that they could be entangled, so they were no longer independent. Again, that will come back later. That is the key to quantum computing, is entanglement, or one of the keys. As a note, Heisenberg also was working in this area. He came up with his famous uncertainty principle, that you can't know the position and momentum of an electron at the same time. This is a concept that they're kind of smeared out. You don't know exactly where they are. He also developed a quantum mechanics theory called matrix mechanics. And that's just another approach to describing what's going on at this microscopic level. And they actually turn out to be equivalent. Right. Over the next 50, 60 years, masses of development in quantum mechanics and a better understanding of how it actually made the world work. But in 1981, there was a conference of physics of computation, and invited to that was Richard Feynman, the famous Nobel Prize winner physicist, who talked about computation and actually touched upon the need for having quantum computation to model the real world. The quote below, I won't go through, but it's basically saying classical theories will not work at the quantum level. If you want to really understand the quantum level, you will have to do it. Other people had suggested similar things before, but he kind of set the seeds here for the need for quantum computing. Back to Einstein, just a comment, because we always think of Einstein to be relativity, special and general relativity. He was there at the foundation of quantum theory with his deductions around the photon. He never liked quantum theory or some of the aspects for it. He liked and agreed that it gave great predictions of things, but he didn't like the randomness of it. The fact that things seem to just occur, and hence his famous quote about God does not play dice. And he spent a lot of time trying to show that this wasn't correct, that randomness wasn't really there. It turns out it is, and the universe has some absolutely random elements to it. So going back to the double slit experiment, you can do the double slit experiment with light, you can do it with electrons. Talked about before that when you do it, you end up with this pattern over here, which is basically peak areas of light and darkness reflecting a wave pattern here. Now, it's interesting, this experiment, because in essence, this wave pattern is a probability curve. It's dictating the likeliness of a photon striking the screen at any one place. So the higher the amplitude, the higher the probability that a photon will strike there. So in fact, we really should talk about the amplitude squared to be the probability. So that tells me that's a high peak. Square it, it gives a high probability that we'll get light, or in this case, electrons striking here. What's more mysterious about the double slit experiment is nowadays we can actually look at firing individual photons or electrons at this double slit screen. Now, say if you fire a single electron through, it'll make a little dot on the screen over here. You fire another one through, it'll make another dot. And you would think at that point, it would behave, because there's only one photon at a time, it would behave more like particles or tennis balls through the slot. And it doesn't. And that's kind of strange, because what's it interfering with to give this pattern? Because that's an interference pattern between waves. And if we fire one photon through, perhaps it has a wave shape to it, a nice sinusoidal wave. What's it interacting with to give this pattern? Even more weird is if you actually look to see which of the two slits it went through, some wonderful camera system that can look at it, as soon as you look, this pattern disappears. And you just get what you would see if you threw tennis balls. You'd get lines down here and a line down here. Even more puzzling, if you sneak away and turn the power off the camera, it magically somehow knows and you get the diffraction grating back again. That is kind of how weird things are at the quantum level. Now, going back to a single electron going through, forget the camera. What's happening, or seems to be happening here, and there's a real danger now trying to interpret things at the quantum level up in the macroscopic level, because, as Feynman said, classical ways of thinking don't actually work very well. So there's a real danger in this. But what seems to be happening is basically the electron is going through simultaneously both of these slits and interfering with itself. And that's where the pattern comes. And what's happening is the electron's in what's called superposition. It's in both states at the same time, going through the left slit and the right slit. And Schrodinger tried to give an example, again, lots of danger messages, but here comes the cat, of how this can be thought of at the macroscopic level. So he had a thought experiment which put a cat in a thick metal box, a flask of poison, and a radioactive element. Now, connected to the flask of poison is a Geiger counter, and if a gamma particle is emitted and the Geiger counter goes off, the cat dies. And if it's not emitted, it's alive. So you set this up, you put it in the corner of the room, and you think, is the cat dead or alive? And you don't know. And in a sense, it can't be known, because there's a probability of a half that it's alive and a probability of a half it's dead. It's in a dual state, a state of superposition. It's both dead and alive at the same time. And taking the quantum point, it's only when we open the box and have a look, does it collapse this situation, this waveform, and either give us a dead cat or a live cat. And that's a really strange sort of thing to think about, that before you look, you have to think of the cat being dead and alive at the same time. And there are many sort of hypotheses of what this actually means. You could think of it like there's almost two universes, one with a live cat, one with a dead, and when you open the box and have a look, you select which universe you're in. Not going to go into that, not too important, but again, what we're seeing here is the cat is in this dual state, this superposition of states. And you can kind of write that down. I'm trying to avoid much mathematics, especially seeing the amount of time that's going by. But you could kind of describe that as a state dead and a state alive. Alpha times state dead plus beta times state alive is the current waveform for the cat, where alpha squared plus beta squared equals 1. So we're basically saying there's a probability of it being dead, probability of it being alive. If we set alpha equal to beta, it's equal probabilities of being dead or alive. And you can attribute, say, a dead cat with, which way round did I do it? Yeah, a dead cat with 0 and an alive cat with 1. So we kind of got a way of representing 0 and 1 by superposition at the same time. As our little cat model, our cat can represent 0 and 1 at the same time, where in traditional computers, you just represent either the state to be 0 or the state to be 1. We've combined the two together in this function. And if we can do that, perhaps we could build a multi-bit, or because they're quantum bits, qubits machine with multiple cats. So I've got 4 cats here. That would give me a 4-qubit machine. If I only had 2 cats, I'd have a 2-qubit machine. 2 is easier. If you've got a 2-qubit machine, you've got 4 possible states that can be in. You can have dead, 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 alive, alive, dead, and alive, alive cat. And we can write an equation out that represents how that combined set of states are at any one time. So again, in the quantum computer, you have to think of our qubit being in all the possible output states at the same time. Again, compared with a classical computer, where you think of it just being in one of those states, you might be saving a 1 or a 2, but here we're thinking about them all simultaneously. So inherently concurrent. Right, that's all very well, but at the moment our bits are independent of each other. So entanglement, which touched upon before, is another special property at the quantum level about actually making 2 elements interact with each other. So one way of thinking about this is, imagine tossing a coin. If you toss a coin in the air, it's in superposition. When it's spinning in the air, it's neither heads nor tails, it's both. But when you catch it, you make a measurement, and in essence, you collapse this waveform that represents the superposition, and you get heads or tails. That's the normal situation. Now, here's the peculiarity when you've got entangled elements. So imagine you've got 2 special coins. You toss both coins and you catch the first, and there's a 50-50 chance that it's heads or tails. Right, you catch the second, and it turns out to be exactly the same as the first when you look at it. So if the first one was heads and you catch the second, it's heads. If the first one was tails, the second is tails. So you've entangled the 2. They're no longer independent of each other. That in itself, it's a bit odd, but maybe you could create some coins that did this. It gets weirder at the quantum level, because if you can entangle, say, 2 photons, and say you took 1 photon to Mars in its entangled state and kept 1 on Earth, if I look at my photon and say measure its polarization, and I get that it's vertically polarized. If you, an instantaneous time later, looked at your photon and it's been entangled with mine, you'll find it's got the same polarization. And what upset Einstein about this was that time delay between me checking mine and you checking yours on Mars could be so small, it's less than the time it would take light to travel from Earth to Mars. And that seems to say something else has gone between my coin or my photon to your photon to tell it what the answer was. That's entanglement. It's a very strange and, as Einstein said, spooky type behavior. It actually turns out it doesn't break rules of the speed of light because actually no information has been exchanged between those qubits. But the key thing here is to realize is actually when you looked at your coin, it's not predetermined what the outcome will be when you look at the first coin. It could be either. It could be heads or tails. So it's not as if you put a red ball in one box and a red ball in another box where it could be red or blue and sent one box to Mars and you opened it and it's the same as mine. It's not predetermined. So entanglement is our second key element after superposition, entanglement. And similar things go on with electrons. You can have electrons that have spin. Spin is an old terminology. Electrons don't really spin, but it's kind of stuck. They kind of act like dipoles. So you can have electrons that seem to point down and electrons that point up, or north and south. When they're in superposition, they're in both states at the same time and will be until they get interfered with, measured. Right. I'll skip that slide. Okay. We now got the concept that we can set certain things in this superposition type state. Say it's an electron that is either pointing north or south, north being 1, south being 0, for instance. In classical computing, we have gates. We have wires and we can do things with them like AND two wires together. If it's a single line, we can knot it. So if we've got a naught, we can make it 1. If we've got 2 lines, one might be naught, one might be 1, we can take the AND of that and we get naught. And that's how we build computers, or more specifically, we use the bottom one NAND gates. We can do the equivalent with quantum gates. So we've got this idea that when we measure something, it will either have a state 0 or a state 1. Well, in our quantum circuit, if we're doing a universal quantum computer, we can set our electron to either, or whatever it is, say electron to state 0, or we can set it to state 1, which is just like putting a voltage on a wire to be on or off. We have gates at the quantum level that can invert it. So if it was 0, we can make it 1. If it was 1, we can make it 0. We have another NOT which can change the phase of our waveform. So I'm going to move to an example of this. And this is where things will probably go horribly wrong. Right. This is called a block sphere, and it's a representation of what's happening with a single qubit. So we can operate on this. Now, at the moment, it's in a state 0. I can then operate on it with a quantum NOT gate and put it in state 1. I can operate it with on 1 with a Y gate. And I can put it back to where it was. Right. I'll set it now to 1 up here, and if I hit the Y gate, I invert it again, and it's not exactly doing what I want it to do, so let's try this again. Right, you'll just see at the bottom, you're getting a phase change. So on a qubit, we have actually more information than we expect. We represent, if I go back to my slides, find them. We're representing our qubit is an alpha 0 plus beta 1, that combined state. What I didn't say was alpha and beta are complex numbers, and they have a constraint on them, as we said before, that alpha squared plus beta squared equals 1, because alpha squared, or the modulus of alpha squared, is the probability that naught's going to occur, and the modulus of beta squared is the probability that 1 is going to occur. That's our state of our electron when it's in superposition. And these gates allow us to manipulate both the sort of magnitude of those probabilities, but also their phase of the waveform, so that if we combine different waveforms, we can get additions and subtractions, interference between them. And that's what these gates allow us to do. But they, to some extent, mirror what we would have in traditional circuits, but with extra capabilities, not just to alter the output value, but this phase information as well. Right, because time's moving on, I'm going to show you a quick quantum circuit, hopefully. Right. So how do we build quantum circuits? One way of doing it is nice and pictorially. So we have 2 qubits here, 1 and 2. And we've got this strange spherical representation. If very quickly you would have seen that up corresponded to 0 and 1 to and down to 1. If we put a NOT gate in there, we can flip it downwards. So suddenly we flipped the value of that from 0 to 1. So just as we would in a normal circuit. We can do more sophisticated things than that. We have, at that point, we know the state of that qubit. It's a 0. But we can have what's called a Hadamard gate that will actually put that qubit into superposition. And this particular gate gives an equal probability, if we were to measure that line here, of it either being a 0 or 1. So it's become a 50-50 chance. And I won't go into the details, but this nice little circuit will let you see the probability of that occurring. So we can build up circuits using this technique. But what we're doing, and I'll go on to the next one. Here's a more complex one. This does modular arithmetic. But what we can do, instead of actually calculating numbers one at a time, we can calculate on all the possible states simultaneously, because we've got this representation, this waveform, that gives us the probability of being in any one of those output states at any one time. So when we do a calculation, say if we were doing Sudoku, and we could set up a quantum computer, we've got a grid, and we've got to fill in the spaces with the appropriate numbers. Well, what a quantum computer could do is to look at all of the spaces with all possible numbers that could go in them simultaneously, and first appropriate circuit manipulation, deduce with a probability what is the likely solution to that Sudoku. So in one iteration, it would produce an estimate of what it thought would be a solution to it. Whereas in a more traditional way, you would have to trial and error, try different combinations. So quickly, we've moved from sort of quantum physics to being able to actually build circuits, at least pictorially, of combining electrons in superposition to do calculations. I've just shown this one. This is modular arithmetic. If I brought it up again, you would see that it can do things like multiply x by 7. I included that, not time to go into detail, because that is a key part to Shor's algorithm for deducing prime numbers. I'll leave in the slides, but I won't go through now. The mathematics behind all of this is actually very straightforward. It sounds complex, but it actually boils down to some simple matrix maths and recall of what complex numbers are. And you can deduce that a lot of these operators are their own inverse, and that actually really helps with doing the computation. So I won't go through that. I just want to introduce one more gate, and that's a 2-qubit gate, and it's a CNOT gate. So we had a NOT gate before, and that just inverted the signal. The CNOT gate is conditional NOT gate, and what that does is it takes a control line, in this case the upper line, and it controls whether the second qubit inverts or not. So basically, if the control line is 0, the second qubit stays as it is. If the control line is 1, it gets inverted. That is a key gate, because suddenly we've got a way of doing something to another qubit from the first. So we're getting them to do things together. And in the modular example, there were examples of that. All right, I'll skip that. Right, one more thing to say on that. That's the key, actually, to entanglement, because if you use a Hadamard gate, that one that puts it into superposition, and you follow it with a qubit, you entangle those two qubits. So they're no longer independent. So it reduces the number of possible output states. It's back to that actually produces the situation like the strange coins, that if you flick both coins and measure one, you'll know the output of the other one when you measure that. That gives you that entanglement. And that is, as I say, the second key element to building quantum computers. I'm seeing the time is going by, so I'll just say a bit about technologies. And again, to me, this is back to Arthur C. Clarke's thing. This is kind of still quite magical. There are a number of technologies being used to build quantum computers. And one of the main ones is superconducting quantum computing. And that basically needs to cool the system down to round about 1 degree Kelvin, which is the one difficulty in making these types of machines, because the actual qubits live on what looks much like a standard chip, but there is a massive bit of plumbing around them to keep it down to that temperature. And you need it at that temperature, or you lose coherence, you lose your superposition, you lose your entanglement. But out of interest, there are 15 countries that have national quantum initiatives looking at how to build and how to use quantum computers. So it's of great interest worldwide. There are two main computers at the moment that you can sort of get access to. There's one called from D-Wave, and that uses quantum annealing to solve the problems. And simulated annealing has been used for many years for solving optimization problems. So something like timetabling in university is an optimization problem with constraints. And the D-Wave, in some senses, is a hardwired computer that if you shape your problem in the right kind of optimization description, then it can solve these. And that has over 2,000 qubits working on this. And you can go ahead, you can get a free account with D-Wave and you can try out some ideas of doing this, some of the examples they've got. So that's there and available, and is being bought by a number of companies. And it comes in a nice black box. Then, as the other example, that's one type of computer, and it's not a universal computer. And then you have, as an example of the other, the IBM Quantum computer, and picture here of it. And all of this is its cooling system, and your qubits are down here. That is programmable through these circuits that I've been talking about before. So this is something you can construct a circuit for and actually run it on their computer. So they have a free SDK and system for doing this called Qiskit. You can put together gates, much as I was showing before. You can do measurements. You can run those on a simulator at IBM, or you can run them on real quantum hardware at IBM. So it opens the door to trying to develop algorithms that can usefully work on these qubits in superposition or entangled to produce answers to problems that would normally take far too long to do. Now, I think I'm probably going to run out of time, or have run out of time, to actually show you examples of that running, which is a bit of a shame because I'll just see. Right, there's probably not time to do this, but I will just bring up, that's my modulo arithmetic type quantum circuit, and on here I can actually run that. As I say, I can set up over here and run that on a simulator at IBM and get out results. And basically that one on a standard computer, it'll use different random seeds to decide what state those qubits come out at and give me results on what it's doing. Or I can set it up differently and I can put it on one of their, if I can find one that's online. I could take that one, I could set it up on there and it'll run on real quantum hardware. That wouldn't be a good one because it looks to only have one qubit. I would need that one with 5 qubits. And what you'll find if you run that is you get ever so slightly different results to the simulator. The simulator tends to behave well, so it may give you a definite result. Whereas you run it on the real hardware, it will probably give you a nice peak, like we have here, telling you what the most likely answer is, but it may give you some smaller peaks that there's a probability that this might be the answer as well. And that's because the real hardware is subject to noise. And that's a drawback of quantum computers. They can be affected by lots of things that create the qubits to drop out of superposition, and that decreases the accuracy of them. So there's a lot of work put in to do quantum error correction. So which really boils down to having multiple, a sort of qubit that you're working with made up of multiple physical qubits to try and do an error correction on those. I will come to an end rather than I have lost my slide. There it is. No, it's not. So the last thing I wanted to say is the sort of where do you go from here? So IBM, you can get a free account. You can develop your own quantum circuits. You can run them on their simulators. You can run them on their real hardware with limitations, not surprisingly, but it doesn't cost you anything. There's a really nice project being done called Raspberry, which basically sets up a Raspberry Pi to be able to do all of that for you. So it basically puts access to Qiskit and the IBM facilities, all the software required onto a little Raspberry Pi. You can even print a 3D model of IBM's quantum computer and get the results out on their Sense hat. So for the price of whatever Raspberry Pi is now, say with the bits, £50 to £100, you can do quantum computing anywhere, and anybody can learn to do it and start to develop algorithms which can then be tested out on real quantum hardware. And I always think it's quite interesting to think that I can run from my kitchen a algorithm I've developed on which actually manipulates electrons and changes their state, puts them in superposition and entanglement on a machine in New Jersey. And I can do that from a very small Raspberry Pi system. When we put the notes up, I put in lots of links. The other great thing about quantum computing is there's lots of information about it, lots of examples. So it's quite easy to get started with it. And although as I put included in here some slides on the maths isn't difficult, and to some extent you don't need it. If you use things like the circuit design systems from IBM or others, then you can ignore some of that maths, certainly till you've got a few ideas down and running. And I've also referenced a few books to look at. Actually, one thing I really do suggest, that's not going to work. This may take a second. Okay, I can't bring it up unfortunately, but there is a really excellent book, paper on the mathematics and background of quantum computers, which is available free from this link. Let's see if this will work for me. Yeah, you should see that. This is a really excellent and supposedly aimed at high school students in the States that explains the maths and ideas behind quantum computing. So it goes into a lot more detail than I've been able to go through today. But it's got things like the time cost. And it's something that, as I say, it's aimed at high school students and early university students. So it is very approachable. And unlike the books, doesn't cost anything. So I'll stop the presentation there. I will try to get back to you. It may not be as easy. Right. There's a lot more I could talk about. As always, I kind of ran over, so sorry about that. I kind of just say, are there any questions? It was only supposed to be a very quick introduction. Anybody want to say anything?
Doesn't look so, apart from thank you.
No, what I'll say is, yeah, it's quite fun to do with quantum computing because it is so different to what we normally do. The concept that you're actually manipulating all the possible states simultaneously rather than looking at one state at a time is a very different way of thinking. But the fact that we've now got IBM's biggest machine is about 50, 60 qubits, usable qubits. They aim by 2023 to have 1,000 qubit machine, and by 2030 a 1 million qubit machine, which means that a lot of these areas, it then becomes very realizable. So the RSA cracking, the encryption, becomes feasible with this. And there are now an awful lot of papers written by people like Deloitte, PricewaterhouseCoopers, people like that, who talk about quantum computing because they can see the impact it can have in encryption, decryption, but also in industries like the chemical industry, where suddenly you'll be able to model things. However, I should say a slight warning to this. There are also people that say that quantum computing doesn't scale, that the engineering will fail. There will be just too many errors when you get large numbers of qubits together because they are unstable. I suspect people like IBM are right and they can do it. D-Wave have done it up to multiple thousands of qubits now, but this is a very specific to purpose machine. So it's not this universal machine that you can program. So I kind of believe it's there. One of the questions also often raised in the press is this going to be the end of Bitcoins? Because Bitcoins use a encryption method, which is basically RSA. The answer is actually, Deloitte do a very good paper on this, a short paper. And the answer is probably not, because they've already changed the way that you pass the encryption information over between users to hide it, basically. You used to have the equivalent to a public key. You only expose that at the very last moment. So you wouldn't give people long to basically break that large number into 2 primes. And one thing you're not supposed to do with Bitcoins is reuse those large numbers. The Deloitte paper is quite interesting because it points out you're not supposed to do that, but people do. And that would become very dangerous because it would mean that, yes, I might only have half an hour to crack it the first time, but once I've cracked it, if somebody else reuses it, I can just pull it out of the library and crack it again. So I might not be able to crack it in half an hour, but next time I can just look it up and I'll be able to access your Bitcoin information. So it's kind of an interesting era. It's at the very start of things, and I found it really interesting looking at it. It's not difficult to design circuits after a while. It's well worth looking at something like Shor's algorithm for breaking a number down into semi-primes, because if you go through it a few times, you start to see how it's doing a key calculation in parallel. And it's a natural result of doing this quantum computing. Should also add, of course, that to do quantum computing, you still need classical computers, because the classical computer basically runs the quantum computer as like an accelerator. So it prepares the data in the right way, and it performs the measurements at the end to get out the results. So it's kind of a bolt-on to existing computing systems. It's not going to replace our classical computers, or not in the foreseeable future anyway. Right, I think I'll stop there. It's probably a good time to stop the recording.
Right, thank you very much, Derek. Thank you, everybody else, for attending.
Right. Thanks, Derek. That was
Okay.
interesting, even for a totally non-computing person.
It's just supposed to get the flavour over.